In a previous video, I talked about the effect of acceleration in the twin paradox. The link to that video is given below. I recommend you watch that video first before you see this video. A twin paradox, there are two twins, identical twins. One twin, let's call her Amy, she stays on Earth, and the other twin travels to a distant star at a speed comparable to the speed of light. In that example I gave, the speed was about 60% of the speed of light. And then the traveling twin returns. When they come back, the traveling twin will be considerably younger than the stationary twin who stayed on Earth. Now, in that previous video, I showed the effect of acceleration in this time difference. The traveling twin, when it goes to the distant star, they have to stop, slow down, stop, and then turn around. That involves acceleration. I derived an expression for the time dilation due to the acceleration. So in that video, let's assume the acceleration of the traveling twin is a uniform acceleration of a in a short time, and they are at a distance x from the Earth. The distance between the star and the Earth is, let's say, x, and the time dilation factor due to the acceleration was derived as ax over c squared, where c is the speed of light, a is the acceleration, x is the distance between the Earth and the star. Now, in this derivation, we used only special relativity. No general relativity was used. The current video, I'm going to talk about gravitational time dilation. That is time dilation due to the effect of gravity using the general relativity, in particular the equivalence principle proposed by Einstein. Now let's consider what Einstein called a chest, which looks like an elevator cab, which is far away from all the planets and stars, so it is not in any gravitational field, it is free floating in space. And let's assume there are two people, Barry near the floor of the cab, and Amy on near the roof of the cab. The height of the cab is x, which is same as the distance between which is similar to the distance between the star and the Earth in the previous video. Now they're not sitting on the elevator, they are all free floating now because there is no gravity. Now we do two things. First, we accelerate the cab. We subject it to an acceleration a. Einstein talks about pulling the cab with your rope, or you can have a rocket fired at the bottom and make the cab accelerate. And let's assume the passengers, Amy and Barry, didn't know that there is a rocket being fired. So when suddenly the cab accelerates, they may think they are under the influence of a planet or star or Earth with a gravitational pull of a acceleration a, which will be equivalent to the acceleration due to gravity. At the same time, let's assume a ray of light, the top, enters the cab at point A, okay, and then it goes straight across the cab. Now, the light ray will not be affected by the acceleration of the cab, so it will tend to go straight across the cab. But the cab is moving up, So for Barry, it will look like the light is tracing an arc, which will be actually a parabolic arc. The equation of the parabola can be derived from this equation. Y equal to ct. So y is this figure, you can see it's a horizontal axis. So the light travels with the speed c. So the y coordinate will be equal to ct, where t is the time measured at the top of the cab, and x coordinate will be 1/2 at squared. You know that from the simple high school dynamics, because there is an acceleration a. It starts from zero velocity, so let's assume the velocity is negligibly small. So by eliminating time t from these two equations, we see x equal to ay squared over 2c squared is the equation of this parabola. Now the curvature of this parabola can be derived approximately as d square x by dv square from the second derivative, and you can see it is equal to a over c square is the curvature of this. Let's assume this arc is very small because the time duration is very small. The radius of curvature rho is 1 over kappa, which is the curvature, which is c square over a. So here I have shown the center of curvature and also the radius of curvature rho of this arc AB. So the arc AB is the arc traced by the light when traveling from point A to point B. Now, Barry is on the floor of the elevator now. He is sitting on the floor or standing on the floor. Now let's assume there's a scattering from point A normal to the propagation of the light. So that light ray will come down and it reaches point C. Then let's assume there's another scattering normal to the propagation using, let's say, a 45-degree mirror. And then that light will from B, it will come to point D. The travel time will be same because they both rays travel through the same distance. So the arc CD represents the light ray as seen by Barry. So when the light was at A, when the ray travels to point C, so Barry thinks the time taken for the light to go from C to D will be much smaller than the time taken for the light to go from A to B. The speed of light is constant both on top and bottom. It is not affected by the acceleration. So if we call d tau is the time elapsed at the bottom for Barry when the light went from C to D, and dt is the time elapsed in the top for Amy when the light went from A to B, d tau by dt is given by the arc length CD over arc length AB, because the speed of light is constant, and it is given by rho minus x, where phi is the angle you can see subtended by this arcs at the center. Now, by cancelling this angle phi, we get the derivation, the expression rho minus x over rho. By simplifying, we get 1 minus x over rho. By substituting for the radius of curvature as c square over a, we get 1 minus ax over c square. So you can see this expression is exactly same as the one derived the previous video for effect of acceleration on time dilation. So we can see the similarity between acceleration and the gravitational acceleration and the regular acceleration or change of velocity. Now when we talk about gravity, we can change a by gravitational acceleration g, the distance x as a height between the observer in the bottom and the top in the gravitational field, and c is the speed of light. This is the expression for gravitational time dilation. This agrees with several approximate expressions you can find in the literature. If you consider the actual gravitational field of the Earth, which is not uniform, and the expression is much more complicated, but if you look at the approximations, they all come down to 1 minus gh over c square. And the beauty of this derivation is this is based on the equivalence principle in the general relativity, whereas the previous derivation in the previous video was just based on special relativity. I encourage you to post your comments about this derivation in the comment section. Thank you.